Okay guys, so the question I asked you was, how can we use the second derivative to help us to figure out if a critical number is a max or a min? Did anyone think of a way that could help us? Let me show you an example. Suppose I have that 2 is a critical number, and I plug the number 2 into the second derivative and find out that it's concave up. How would that help? If I knew 2 was a critical number, meaning the slope was 0, I plug 2 into the second derivative and it's concave up, what's that going to tell me about that point of 2? It's going to have to be what? A minimum. So what if I had a critical number of 3, I plug it into the second derivative and I find out it's concave down, what is that going to tell me about it? It's going to have to be a maximum, right? So that's what this is saying. We're trying to figure out how can we use the second derivative to help us to find maxes and mins. So we find the critical numbers by setting the first derivative equal to 0 and solving. We find the second derivative. That's going to tell us concavity. If that second derivative at the critical number is positive, that means it's concave up. So that means we have to have a minimum. If the second derivative at the critical number is negative, it's concave down, so therefore it's going to be a maximum. Concave up is going to result in a minimum. Concave down is going to result in a maximum. If the second derivative at that critical number is 0, then the second derivative test fails, and we have to go back and do the first derivative test. All right, so now I'm going to give you guys an example. So let's say that our critical number is 4. I plug it into the second derivative and I get a positive. Write down whether it's a max or a min. And now, suppose that we have a critical number of 6. I plug it into the second derivative and I get a negative. What does that mean? So what do you think on the first one? Nick, what do you think this one's going to be? And why? But more specifically, why? What's the concavity if it's a positive on the second derivative? It's concave up. It's like this, isn't it? So therefore it has to be a minimum. And so everybody should have for this one a maximum, right? And you can see why that would be confusing. Like if I just said, okay, the second derivative's positive, and you get a minimum. Like that's not really intuitive, is it? I mean, a lot of people would say, oh, if it's positive, that should be a max. But no, it's because the concavity is positive. So it's upward, and so we do have a minimum. So that can get confusing, and some people do it backwards. When they get on a quiz, they just get a little confused and write those two the opposite way. Don't be one of those people. All right, so for each of the following, find extrema by using the second derivative test. If the test fails, then use the first derivative test. All right, so let's go ahead and find the first derivative here. Madison, what's the first derivative? And so then I have to set that first derivative equal to 0. What do we get for x then? Joe? Take the 2x over, divide by 2. So it would just be 4. So 4 is going to be our critical number. Now we're going to take our second derivative. Jackson, what's the second derivative? -2. What that tells me is there's no x with this. So the second derivative is always negative. So that means that this function is always concave down. That's what that's telling me right there. So my critical number was 4. Every value, including the critical number, has a negative on the second derivative. So what does that mean then about this point at 4? What's it going to have to be then? It's going to have to be a max. So we have a max at 4, comma, plug that back into the original. 4 squared is 16, that's negative 16, plus 32 minus 3, and that's going to give me 16 minus 3, that's 13. In calculus, you should start making connections to other things that you've learned in math. Can anyone tell me, by looking at the very original part of this problem, why it makes sense we'd have a maximum? What's that, Haley? Right? And what kind of shape is it if it's a negative x squared? Parabola that opens down, right? So wouldn't that make sense that we'd have to have a maximum somewhere and not a minimum? Okay, that's what we're doing. All right, let's look at this example. So we're going to take our first derivative. Our first derivative is negative 15x to the 4th plus 15x squared. I have to find my critical number, so I'm going to set that equal to 0. I'm going to factor out a negative 15x squared. That leaves me with x squared minus 1. Now we have to set each of these equal to 0. Sarah, what are the critical numbers then? Don't forget the 1 and negative 1, right? And that's because this would factor down to x plus 1, x minus 1. So we have 3 critical numbers. I have to find the second derivative now to do the second derivative test. So my second derivative is going to be negative 60 x cubed plus 30x. I'm going to factor out a negative 30x. And you get 2x squared minus 1. So solving this, we're going to have critical, what happened there? That's not supposed to be the answer. Hold on. Is that right? That's not what I got the last class. Negative 15x to the 4th plus 15x squared. That derivative is negative 60x cubed plus 30x. I'm factoring that out. 2x squared. Okay, that's right. Okay, so what are oh, never mind. Okay. So we now have to plug our critical numbers into our second derivative. I don't need to set this equal to 0. I'm sorry, I was thinking I was finding points of inflection. We're not finding points of inflection. So we have our second derivative, we have it factored, so we're going to plug in our critical numbers directly into that second derivative. So plugging these in, I'm going to have negative 30 times negative 1, that's going to be positive. Times this, negative 1, that's going to be 2 minus 1. So that's going to be positive, yep. So that ends up being a positive for sure, when we do that. When we plug in 0, though, I get 0. So this one, where I have it concave up, what are we going to have where we have it concave up? What's that mean this is going to have to be? Minimum. When I get 0, what did we say up here? When we get 0, what happens? The test fails. Fail. When I plug 1 into that second derivative, I get a negative times a positive. That's a negative. That means we're concave down, so what do we have? A max. Now, here's the problem though. The test failed here. That means I have to go back and check this with the first derivative test. See, this was the second derivative test. I have to go back to the first derivative test. This is where I make my intervals. So I'm going to have to go from this critical number to there, and I'm going to have to go from 0 to 1. I'm going to have to use those intervals. I'm going to have to plug in values, test values, back into the first derivative now, because I want to see, maybe this is a max or min, and it just happened to fail. So plugging negative 1/2 back into that first derivative, that's going to give me a negative. Negative 1/2 squared is 1/4. That's going to give me a negative. So I get a positive. 1/2 is going to be the same thing, because whether I have a negative or a positive, if I square it, it turns positive. So I'm going to have a positive times a negative, and then it times another negative. So that's going to be a positive. So if my function goes from increasing to increasing, do we have a max or a min? No. So 0 is nothing. It's not a max or a min. Maybe it's a point of inflection, like I started to find up here. So we then have a minimum at, plugging that back into the original, negative 1, that's going to make that a positive and that a negative, so it's 3 minus 5, so it's going to be negative 1, negative 2, and we're going to have a maximum, when I plug in 1, of negative 3 plus 5, and that's going to be 1, 2. Okay? So going back through the methods, just real quick, what do we find first? We have to find the first derivative, which will tell us the critical number. Then we also have to find the second derivative, right? We don't need intervals. Do you see the difference? Like when we did the first derivative test and the concavity test, we always used intervals, didn't we? With the second derivative test, though, we just plug these critical numbers right into that second derivative. And that's going to tell us whether or not we have a max or a min. So without looking, if the second derivative is positive, what do we have at the critical number? Minimum. Okay, very good. So you guys have some problems to do up there.